everybody. I'd like to start today by sharing a story with you about when I first started at Goldfields. One of the challenges that I faced about 2.5 years ago was how to get more than 40 exploration geologists, most of whom had little to no geochemistry experience across 4 different mine sites, to effectively use multi-element geochemistry. And you probably know companies go through phases, and at this time, each site was doing its own thing in a limited way, or not really using multi-element geochemistry at all. Additionally, there were 4 different databases in various stages of upgrade, with a huge amount of data from more than 40 years of sample collection. It was a bit of a quagmire, and if I'm really honest about it, it was also a bit daunting, as you can imagine. But it was up to me to come up with a system to get everyone on board and using multi-element geochemistry effectively. So within the first 6 months on the job, I had run training courses for all the geos, and I had run everyone through ArcGIS and basic principles of geochemistry and its use in terms of classifying rocks and alteration and Pathfinders. And what I observed, though, was that while most people were really keen during the training and afterwards, I wasn't seeing the application of the multi-element geochemistry in the project funding requests and the closure reports coming through from the geos. I also noticed a common comment was that the process to access and to use the data took too long, and people didn't know really where to begin. So eventually, some might even say rather sadly, I realized that I was not going to be able to turn everybody into an applied geochemist. So I had to reevaluate. I wanted the geos to use their multi-element geochemistry data to consistently classify and quantify their rock compositions, alteration, use their Pathfinders, as well as the ASD data that we get. My boss, the VP of Exploration, was much more focused on accelerating discovery by identifying better targets faster. So the solution I came up with was to provide the geos site-specific, custom-built, multi-element geochemistry packages in ArcGIS, which is a user-friendly platform most geos already knew how to use. You can see I've also got a little plus there, and that's because I also decided to provide the geos with ArcGIS files that contain the same data sets and interpretations for those that were able and interested and wanted to dig into their own specific data, project data a bit more. So I just want to point out here that I'm going to be speaking mostly to the setting up and application of multi-element data, not our gold data, which we have a different ArcGIS setup, which is outside of the scope of this talk. So where to start? Well, of course, we start with the database. So the first thing I needed to do was to sort out all of the problem data in the database, and Feed, you did a great job of setting this up for me. So I decided that most of the problem data could be classified into one of 5 categories, and I've got them listed here on the left-hand side. And I identified most of these issues using the data doctor in ArcGIS, and importantly, I tagged them with a priority so that they could be filtered out of any export. So not deleted, but filtered out. And I have an example here on the far side for problem data in arsenic from one of our mines, from St. Ives. So arsenic is a classic problem child. Excuse me. Everyone loves to use it, but it has a long history of being collected, as it was often one of the first elements that were analyzed back when elements were just collected individually or assayed individually. So you can see here at the top, we've got some samples here that have no coordinates. So regardless of how fantastic the assay is, it's totally useless. We also have some nonsensical values of 0, as well as some large, very large negative numbers. Below that, we've got some old database codes, as well as a really large number of samples with old historic detection limits of minus 100 ppm. So I know everyone's holding background concentrations of crustal arsenic in their head. So I'll remind you, it's about 1.5 ppm. At St. Ives, it's around 6 ppm. So if you do what Fiona said, which is what I would recommend as well, which is replace your detection limits with half your positive value, you're going to end up with a false positive. And we don't want that. So I also used probability plots of each element, colored by the lab method where we had the metadata, to identify unit conversion issues, historic detection limits that were way too high or possibly not marked by a negative value in the database, which can be common, as well as incompatible digests. And it's important to tag these out because they can create data issues for the unwary data user. Another huge frustration that myself and a number of the geos regularly experienced in the beginning was getting the data out of the database in a consistent format. So the situation would go something like this. I'd get an email from the geo on site saying that they wanted to get some help working up their data. Fantastic. I'd email about them back and say, send me your data and I'll have a quick review before we get started. Inevitably, I'd look at it and there'd be something askew, something would be missing. It had to go back to the geo. And then the geo was off swing. So you can see we'd go back and forth a number of times. And with the geos working on swings, weeks would go by before we would get started. So I realized what we needed was a standardized export across all the sites. So I teamed up with the DBAs and for each site to create a multi-element export that was immediately ready for importing into ArcGIS, which is the software that we use for interrogating our geochem data. And it contained all the data that we might need to use when we're doing a workup. So the result is what I'm showing here, and it's what I call the ArcGIS Ready Export. And it has 6 data groups. So the first one there has all the drilling metadata, importantly the project code for the geos to filter their projects by, as well as desurveyed X, Y, and Zs. The second one is all of our elements, and I've put them really imaginatively in alphabetical order, so they're really easy to find for everybody, and I've also put them all in the same unit, so we can get to recognize when something's gone askew. We also collect ASD data as part of our routine multi-element package, and that's collected by ALS and interpreted by OzSpec. But we get 2 sets of data back from that. We get our minerals and our mineral contribution, as well as mineral phases. And then we also get what I call the spectral parameters, the more traditional ASD data. And then I also asked the sites, what logging metadata would you like to see to coordinate and to combine with your geochemistry data? And then finally, the multi-element interpretations that I do for the geologists regularly. So importantly, this export allows the geos, in one click, to use their logging and their geochemistry together, which is very powerful. And it's the same every time, so very easy to pick up if something's gone amiss. So the next step in the process was to actually create meaning. So we want to transform the numbers into rocks and minerals. So as we've heard today, and I'm sure many of you know, one of the really powerful things we can do with our multi-element geochemistry is classify rocks, which we commonly have heard is called lithogeochemistry. What I also experienced was people often shorten this to lith or litho, which also happens to be the word many people and also many databases use for logged rock type. So this led to more than one confusing conversation. So I created a unique multi-element labels that emphasized that the source of the classification was from multi-element data, ME, and that the classification provided a chemical composition. And the name had to be short enough to actually work with the database and the GIS. So we came up with ME Rock Comp. So working with Scott Halley, 3 site-specific workflows were created to classify the rock types using immobile trace element ratios based on rock-forming principles. All the samples with the required elements were classified for the major rock types, and more detailed classification was provided for the more prospective rock types, or at least what we thought. The ME Rock Comp classifications were given local stratigraphic names where it was reasonable and where it was possible, and I classify this data for the geos, and it gets uploaded to the database about between every 1 and 3 months. Similarly, for the ME alteration classifications, we have 3 site-specific workflows that were created to classify all the samples that had the prerequisite of the ME rock comp. And this is done systematically using the diagram that I show here. It's the sodium over aluminum versus potassium over aluminum diagram, commonly known as a feldspar control diagram in ArcGIS. So depending on where the sample sits compared to a background population, it can be assigned a sodium or a potassium bearing mineral name. And we do this assuming that any sort of metamorphism is isochemical. And again, I produce these classifications on a regular basis for the geos, and they're uploaded to the database. And of course, we can't forget about the important Pathfinder elements. So what I noticed was that the Pathfinder elements are part of the periodic table that the geos go to often, as that it's relatively easier to interpret. But the common question I often received from a lot of the geos was, well, how much is enriched? Like, what's an anomaly? So to answer this, I determined site-specific background values by looking at all of the median values for each of the Pathfinder data, from only though choosing samples from sap rock and fresh and at crustal values of gold. And this is one of the benefits, I guess, of having large data sets to draw from. So this gave me the background values. And from here, I was able to determine increasing cutoff values in steps or times background values above a certain threshold, with a threshold of about 10 times background being something interesting and worthy of further investigation. So it's important to note, too, that this is done on a tenement scale, and that, of course, local deposits will vary in terms of their concentrations. But the idea is that it gives the geos a common place to start from and to better interpret the concentrations that they are seeing in their data. And the final step was to bring all of the key geochemical interpretations and cutoff values into one user-friendly platform, the multi-element GIS package. So nothing in life is done in isolation, right? And this whole project relied not only on myself, but also our site DBAs, site contacts, which Chris Shanley is one of them, he's sitting in the audience, hats off, and our GIS specialist. I asked our GIS specialist, Amanda Griffith, to put together a couple of slides, one of which you're looking at here, which summarizes how she and the DBAs linked the database and the GIS together to create the multi-element package. So this is not my area of expertise at all, so let's just walk through this slide together. So the ME data itself is stored in an SQL server with either an acquire or data shared front end. A separate database B is used to create views that represent the GIS layers from the linked databases. C then are the shapefiles of individual layers that are created with Python from the views. And then gridding of the resulting shapefiles is conducted in GeoSoft Oasis Montage. And this process can be automated. And the ArcGIS controls the symbology. So why was the system set up like this? Well, the separate SQL database houses the queries, and this ensures that we use less of the DBA's time because they actually have lots of other things to do for us besides running exports. And it also retains permissions on the main drilling database itself. We found that straight linking to the database was very slow, aggravatingly slow. So the shapefiles on each site server were used. And additionally, this allows updating of the shapefiles in the background, even if they're opened by a user. The GeoSoft gridding was used as it's considered superior to Spatial Analyst, and the task scheduler and batch files allow full automation of the process. So you can see that this part is a critical section of getting it out to the geos on a regular basis. So how was all of the data laid out and organized? Well, we decided that it would be easiest for everybody for importing and updating if everything was kept under one master layer. So we've got the geochemistry layer there. And this would involve less searching and messing around for layers and versions and whatnot. And under the master layer are 6 key layers themselves, which I've got listed. We also wanted to take the geological context of the multi-element sample into consideration, because that's important. And we had several long conversations debating about how many regolith layers should we have, or how few layers should we have to break the data up into. In the end, we decided that the critical boundary for us, because we're a very drilling-centric company, was whether the sample was in regolith or was it in sap rock and fresh. So we included that break in the data sets, in each of the data sets, which you can see. So under each of the 6 key data headers, the individual multi-element interpretations are found, which you can see here. So the ME rock comp and the ME alteration have consistent naming and color attributes, which makes everyone's lives much easier. The Pathfinders are provided in 2 similar but slightly different viewing options. One is a grid, which I like for assessing the size of anomaly. This highlights the spatial trends of the highs and lows in the data, regardless of how enriched or depleted they actually are, whereas a times background map informs the geos about how significant the enrichment is in terms of absolute times above background. So like I said, they're slightly different, but to me they emphasize slightly different aspects of the data, both of which are important when we're vectoring. I wanted to include all of the other elements as well, so that all of the data was available in one place. If a new idea came up or a geo had something that they wanted to test, they wouldn't have to worry about importing everything. It would all just be there, ready to go for them. I mentioned that we also collect ASD data as part of our standard ME package. So for each of the mineral species reported, I've divided the spectral contribution results up into consistent color stretches. And for the 5 minerals that we receive mineral composition data, I divided up the wavelengths into meaningful ranges and added an interpretation tip for the geos so they can relate the wavelengths to actually the composition of the minerals, because it's hard to keep all of that in your head. And of course, the idea is that in addition to pulling together all of the geochemistry in one place, the geos can now easily use their geochemistry together with other key data such as structure, mapping, geophysics to identify targets rather than just chase anomalies. So I'd like to end my talk with a few examples from geos on site themselves about how they're using the multi-element packages and the data. The first example here is from Jay Stafford. So Jay commonly uses her Pathfinder element layers when she's doing early stage exploration. And she's outlined here for me her original data collation workflow. So this is not interpreting the multi-elements into litho or alteration. This is just getting the data together. It would take her 3 to 4 hours and 4 software programs, and I'm sure more than one headache. And so consequently, she would only do this every second swing. Now, with the new workflow, it takes her about 5 minutes, 1 software program, and she does it at least once a swing. So this is a huge improvement, and in her own words, it allows her to focus more on the geology and less on fussing around. So it saves time and money, and it means the geo is spending more time doing their job, focusing on geology, and less time managing data. The second example is from Matt Boundy. So Matt was working on an area called Wonderwall. The area was covered in transported material, so it didn't allow for a lot of surface mapping. And the original geology map was based primarily off of magnetic images with some limited mapping from other areas. The regional geology map showed only a single unit of ultramafic, the Agnew komatiite. So during drilling, Matt logged what he thought were 2 komatiite units. Given the limited information in the area, he also asked me to check out the chemistry of the ultramafic units to see if I could see any evidence for 2 units. And sure enough, the ME rock comp showed not only 2 ultramafic units, but also a thin wedge of Mount Good basalt between them. So we had defined the Wonderwall shear, which is important for understanding where the gold was occurring. But Matt also noticed when he was logging that there was another unit in the hanging wall and the footwall, and he couldn't really resolve it from the core. He wasn't sure, was it alteration, was it another unit? So being an excellent geologist, he logged it as a separate unit, and he collected multi-element samples. So it turns out, when he compared the ME rock comp and the ME alteration samples to his logging, the unknown unit was actually moderately to strongly albite-altered ultramafic of the 2 units that he had previously visually and geochemically picked. So using the logging and the geochemistry together, Matt was able to increase his geologic understanding of his area and explain the location of the gold, which I haven't shown. We now have a targeting aid where we can go looking for fault offsets between these 2 ultramafic units in the air core and the RC drilling, where the textures may not be as evident as in the drilling. And my last example is from Amberly. Amberly had completed a full-field air core program and was working up her bottom hole multi-elements in gold. To do this, she wanted to use multi-element interpretations together to understand the structure and the geology in the area to piece everything together, so she could rank her targets in an informed manner from a large area. So in addition to looking at the gold results, Amberly looked at the ME alteration and saw that there were several areas of broad interest that were potassic and sodic altered. To add to the story and to continue to stack the evidence, she also looked at spatial trends of all the Pathfinder elements, and we saw there was a distinct linear spatial trend running along a basin margin, as well as some clusters in some of the Pathfinders. And Amberly also looked at our good old friend arsenic and with the location of structure. And so patterns were starting to emerge. So using the MEGIS package, Amberly was able to interrogate several layers of multi-element geochemistry relatively quickly and document the evidence. She was also able to interrogate the geochemistry with other key data, such as structure, and build a story to decide on how to follow up her targets, of which we see here that the Jasper one was ranked the highest, using all the available evidence. So finally, to wrap up, while a comprehensive multi-element GIS package takes some time and commitment to set up, I believe it becomes an invaluable tool for transforming numbers into accessible minerals, rocks, and models. You've seen here that it can be easy to use, it increases efficiency, provides consistent, high-quality interpretations, it can effectively combine historic and new data, It aids with ASD interpretation, and it allows geologists to get on with their job and proceed to targeting or other tasks. And the next step for us is actually to build in the automation of all the classification that I do manually for the geos. So that'll be next year. Thank you.